Okay, I think this is part 4 of this walkthrough of the physics IAL exam for Unit 4, Further Mechanics, Fields and Particles. The first section was multiple choice, then I went through section B in 2 separate videos, and we've done up to question 15, I think. So we're going to zoom ahead. Don't forget to like, share and subscribe. Yeah. Because I don't always know when I'm going to do the next video. It depends when I get free time. So we've been through all the multiple choice. We went through 11, 12 and 13 in the first of the section B, and then question 14 and 15, which was about further mechanics, conservation of momentum, conservation of kinetic energy, in the part 3 video. And then we finished on question 15, which was about centripetal force with the toy car moving inside the sphere. It's like working out where it's at the top, when it's at the bottom, and how the contact force changes from the top to the bottom. So I think what I didn't clarify in the final 6-mark question, which was here, so this continuation of the last part, if you like, when they're talking about the magnitude of the force exerted by the ball on the car, they're talking about N from this equation, because the centripetal force is constant. Yeah, the centripetal force depends on the velocity mv squared over r. So we're talking about, when they're talking about what force they want to say, how it varies, we're talking about N. Yeah. So when you're talking about N, yeah, the normal contact force changes vertically at the top and the bottom, because F equals N plus W at the top, yeah, and F equals N minus W at the bottom. F and W don't change, but N does. So at the bottom, yeah, N will equal F plus W. So the normal contact force will be N will be equal to F, which is F equals mv squared plus mv squared over r. It will be plus the weight, yeah. So that will be a bigger contact force, whereas at the bottom, or at the top, N will be equal to F minus the weight. So the contact force at the bottom diminishes, okay? So that when the car is at the top, N is a minimum. We should really say N is a minimum rather than the F, because I used F interchangeably with this centripetal force. So I hope that clarifies that point. So when they're talking about the magnitude of the force exerted by the ball, they're talking about N each time. Okay? So just make sure you've got that clear in your minds. And this is a common question. So I probably would lose one of my clarity marks, because they give you 4 marks for explaining all these 6 points maximum, and then 2 marks for how clearly your reasoning is. So I probably didn't explain it as clearly as I should have. Apologies for that. Okay, so then going into the next question, we've gone into the magnetic field area. So once again, don't forget to like, share and subscribe. I keep having to tell you this because I notice I do get, for example, if I've had 900 views on a video, I'll get like 50 likes. That means 50 likes. So really we want more than 50 out of 900, or 50 out of, it's about 5%, isn't it? So we want to have more likes than that to go up in the algorithms. So a search coil, yeah, is used to investigate the magnetic field. Obviously, if you put a coil in the magnetic field, there will be an EMF induced in that coil depending on the angle at which it cuts through the field lines. So it's called a search coil. It consists of a coil of thin copper wire connected to output terminals, as shown on a diagram. Yeah. And the student placed the coil in the magnetic field with the axis parallel. Yeah. The axis was parallel to the direction of the magnetic field, as in the first diagram. Okay, so the magnetic field is going through the coil, yeah. And then in the second diagram, yeah, the coil was rotated through 90 degrees, so the axis was now perpendicular to the direction of the field. So obviously in the first direction you get bigger flux linkage than in the second direction. So as the coil was rotated, a potential difference was detected across the terminals. So as it's going from one position to the next, you're going to have change in the magnetic field cutting through the coil, and that rate of change of cutting through the flux is called the flux linkage, and that is what determines the EMF induced. So you've got to be able to explain that. So I put the EMF induced is equal to the rate of change or the rate of flux linkage, yeah, when wires or the conductor, the coil, the search coil cuts the lines of magnetic flux, and EMF is induced. So it is that change, that movement from one position to the other by Faraday's law. Okay, so this is Faraday's law, and you'll get the 2 marks for explaining those two sentences or phrases where I've put the ticks. It then says, show that the initial value of the magnetic flux in the coil is about 9 times 10 to the minus 5 Webers, yes? So that's phi in the equation I've shown you. So this is the equation you want to use. We need to have the magnetic flux density, which is given to us, and we need the area, which we can determine from the diameter of the coil. Okay, so this allows us to work it out. So first of all, the area is pi d squared over 4. So then if you get it's millimeters, so you've got to change it into meters. So it's pi d squared over 4. I forgot to put the squared in there. So that should be a squared. And if you do this right, you will get, just checking with the marks and I didn't make a mistake. Yeah, 0.025 is same as 25 times 10 to the minus 3. And if you get that, the squared right, you will get 8.85 times 10 to the minus 8.84. I put 8.8 roughly to 2 significant figures. So this is 3 significant figures, and you should probably change it to 2 significant figures because most of the data is not. So this would actually be approximately equal to 9 times 10 to the minus 5, and that's in fact, yeah, that's in fact equal to 1 significant figure, isn't it? So they only want it accurate to 1 significant figures. So we should to put this to 1 significant figures. It's correct. So let me just rub out this, yeah, and here I've got my original answer to 3 significant figures. So it's good to show that you know how to convert it to 1 significant figure. Okay, so I'm just checking that I've got the area right. I did. The area is calculated correctly according to the mark scheme. Part C then gives you a graph. The graph shows the magnetic flux in the coil when the coil was being rotated, yes, and you can see that the value we just calculated was around here, was approximately 9 times 10 to the minus 5 Webers. Okay, so Weber is Teslas times meter squared. Now, so what they want us to do, the graph shows the magnetic flux in the coil as the coil was rotated, yeah? And they want you to determine the maximum PD. Well, the maximum PD is the maximum gradient of the graph. The maximum gradient of the graph can be calculated, as I've shown you here, by the use of a tangent. Okay, so the use of a tangent, you can then get the maximum PD, yeah, and you'll be able to show that it goes up 8.84, yeah, up to the maximum point of the graph, but I've drawn a tangent which goes all the way up to 10, yeah? So here is 10, and it took, and the delta y, or delta x, is 0.02. So I know this is 10 up there, and this is 0.20, yeah? So 10.00 and 0.20 is the gradient of values that you need to work out from. So if you do that on your calculator, you'll get the maximum gradient of the graph as being the maximum PD, because that's the greatest rate of change in the flux. Okay, and you get 5 Webers per second, and then once you know that, then you can put it into the equation here, which the EMF is the rate of flux linkage, dN phi by dt, which is 5,000 times 5.00, yeah, the rate of change will give you a value of 2.5 volts, again to 2 significant figures. So that's how accurately I think we can quote the data, yeah. So the 5,000 comes from, oh yes, the 5,000 is a number of turns, so each of the turns is changing at a rate of 5 Webers per second, 5,000 of them, so you multiply the value of the number of turns, n by the phi by dt, which is the gradient, so d phi by dt is what we got here. Oops, apologies. D phi by dt is what we have on the graph, because, oh my god, I keep doing the same mistake. I'm on the pen mode. Okay, move it up. So here you see this is equal to, this is phi, yeah, this is t, so the rate of change of phi against time is the gradient, d phi by dt, okay, so the gradient, yeah, is equal to the change in y-axis, which is d phi over dt, okay, the gradient of this curve. So dy over x is d phi by dt, and if you have done that correctly, you've got 5, and you can work out the EMF. Then it says the output terminals of the coil are connected together, so then you're going to get a current, because before it was just an EMF. Basically the output of the terminals connected together means you've got a complete circuit. When the coil is in the magnetic field, the diagram shows a cross-section through one turn of the coil. So imagine you're just looking at one turn of the coil. X is on one side of the coil, so you basically got the current shown to go into the page at X and coming out of the page at the bottom of the coil, so you could call that Y. Okay? The coil is rotated as shown clockwise in the magnetic field, causing a current in the coil. The student states that the current at X is into the page. Well, how can you check that? Deduce whether the student's statement is correct. Well, it's at you, but they want you to refer to Lenz's law. Okay, so if the current is there, then you've got to explain it in terms of Lenz's law. And Lenz's law states that the current that's induced must act against the cause, the change that's causing it. Okay, so that's how deep they want to go into it. That's why it's 4 marks. Okay, so let's just see if we can break this down for you. All right, so the student is correct. We can tell that the student's correct just by saying that you could use Fleming's right-hand rule. So if you use Fleming's right-hand rule, and you know the field direction is downwards and the current is going into the page, yeah, so you have to put your fingers in the right direction, which will show you that if the coil is turning clockwise, the current will be induced at X to go into the page. And once you know that, so we already know that the student is correct, but they want us to refer to Lenz's law, okay? So by Lenz's law, the magnetic field produced by the current, which is, as the student correctly states, is going into the page X. Then if you use the left-hand rule, yes, with the current going into the page and the field being downwards, then the force due to this bit, I'm going to do it in a different color, the force being due to this way, so due to the left-hand rule, oh, I haven't changed the color, okay, this is due to the left-hand rule, this is Fleming's left-hand rule. If the current is going that way, this current that's being induced will also produce a force against the motion. So this is the force by Lenz's law, yes, by Lenz's law, if the current is going in the direction shown there, it will oppose the clockwise motion, okay? So that would be correct according to Lenz's law, that, as I've said, by Fleming's left-hand rule, the force on the current at X is to the left, which is against this motion, so student is correct that that must happen, okay? So you could also reverse the argument saying that for the current to be induced, it must create a force against its motion that's causing it, yes? So you could go in the opposite direction, but you can also use Fleming's right-hand rule, check if the student's correct, and then explain why it does produce, by Lenz's law, a force that's opposing the motion that created it, okay? Hope that makes sense. So these are common questions in the exam, and I think this is quite a good one to learn from. Okay, so that's taken us to the end of question 16. Question 17, we're trying to go through this as well, is about electric fields. So this time, potential difference of 5,000 volts is applied across two metal plates. So you've got 5,000 plus volts on the left plate and 0 volts on the right plate, okay? So that depends on how you set up your circuit. So it could be that the 0 plate is earthed and the other plate is connected to a 5,000 voltage power supply, okay, or source of voltage. A sphere with a conducting surface is suspended by an insulating thread and touches the positively charged plate as shown, okay? So obviously that sphere will become positively charged, okay? And eventually it's going to be repelled by the positive plate that caused it to become charged, okay? So it tells you the sphere becomes positively charged. They then want you to simply complete the diagram. They've drawn you the circle on your paper, if you've got a blank copy, to show the electric field around a positively charged sphere. Where the reason they're telling you is positively charged is because then they want to see if you know which direction to draw the field lines in. So if it's a positively charged point source or a small charged sphere, then it will be a radial field with the field lines going outwards, and they will give you a mark for drawing at least 4 radial lines going outwards. And really you should space them equally to get the second mark, and the arrows should be pointing outwards. So the field lines always go from positive to negative, okay, so away from positive. That's how you get the 3 marks. They just want to test that you can draw radial fields, okay? The next question is then show that the charge on the sphere is about 10 nanocoulombs. 10 nanocoulombs means 10 to the minus 9 coulombs. Okay, so don't forget to read these prefixes accurately. So we know that the voltage at the surface of the sphere, remember it was charged by 5,000 volts, so we know the potential at the surface of the sphere is 5,000 volts because it will be charged by the 5,000 volt plate, and the radius of the sphere is given as 20 millimeters. So we can use the equation which is given to you on the equation sheet as the potential equals the constant of proportionality which is 8.99 times 10 to the 9, and this is given to you also on the equation and formula sheet at the back. You change the subject to make Q the subject. We know K. We know Q. No, we don't know Q. Sorry, we know K. We know the voltage and we know the radius. So we know everything on the right-hand side. Put the numbers in, and it's a 2-mark question. You'll get the charge will be 1.1 times 10 to the minus 8, which is approximately 11 nanocoulombs, which is approximately 10 nanocoulombs if you're doing it to one significant figure. Okay? One significant figure is what they want you to do it to, because they're saying about 10 nanocoulombs. So that's to one significant figure. One significant figure. Okay? In fact, all the values are only known to one significant figure. So there's no point in having a decimal place here. This would be to 2 significant figures. So it's important that you understand the significance of significant figures. Okay, so we've done part B. Part C then says the sphere moves away from the positive plate. Why? Because they're both positive. Okay, and it comes to rest at an angle of theta to the vertical. Show that the horizontal force on the sphere is about 5 times 10 to the minus 4 newtons. So that will be the horizontal force. So we know that there's 2 forces acting on it. The horizontal force of repulsion due to the positive sphere in the positive field, or away from the positive plate in the field. And we know that it must have a weight downwards. Okay? So if we want to know what the horizontal force is, you can, first of all, you know the field strength is equal to the voltage divided by the separation, and they have kindly given us the separation between the plates. So this is the equation in a uniform field, and a uniform field is the field in between 2 plates. Okay, so that would be the field in between 2 plates. I'm going to rub them out so they don't get in the way of my diagram. Okay, so you know that in such a situation the field strength will be equal to 5,000 divided by distance between the plates, which is 10.5 centimeters. Okay, and that gives you, through 3 significant figures, a value of 47,600 volts per meter, which is the field strength in volts per meter, because you can also have it in newtons per coulomb. And then you want to work out the horizontal force, and you know that force is equal to the charge, which is in this case the charge on the sphere, yes, which we worked out in the previous question as 1.1 times 10 to the minus 8 coulombs to 2 significant figures. And once you multiply it by the field strength, 47,600, yes, to 3 significant figures, you know that the charge times the electric field strength must be equal to the horizontal force on the sphere, which gives you a value of approximately 5 times 10 to the minus 4 newtons, again to 1 significant figure, yes, and we calculated it to 3 significant figures. Okay, here our accurate calculator value was 3 significant figures, and we have proven that it's approximately 5 times 10 to the minus 4 newtons to 1 significant figures. They then want us to show, well, that creates the angle of 1 degree. And this time they give us that the mass of the sphere is 2.7 grams. So if you think about it, what you've got is the angle is caused by the horizontal force to the right and the weight downwards. So you've got a right angle triangle where the angle is theta, yes, which I have drawn for you in this part of the question. So here's the right-angled triangle where theta is approximately 1 degree. We want to prove it. Yes, show that means you've got to prove it. We know the weight is 2.7 times 10 to the minus 3 because it's in grams, multiplied by 9.81. So you know the weight is much greater than the horizontal force, which is why the angle is small. Then tan will be the opposite, which is the smaller FH over the W, which is the force downwards, and you get tan theta 0.0198, which gives you a theta of 1.13 degrees. That's to 3 significant figures, yeah? And you want to show to 1 significant figure, yes, that the answer is approximately 1 degree. Okay, there's the 3 marks for that. Now it says a second identical charge sphere is held in a fixed position. Okay, so there you have an insulating sphere diagram. 2 spheres shown. Okay, the first sphere attached to the insulating thread is placed near to the fixed sphere. The spheres exert a repulsive force on each other. Okay, because they're identical, so they're identically charged. So we know the force between them is approximately 5 times 10 to the minus 4 newtons. That's to 2 significant figures. They've given it to us. 2 significant figures. Calculate the distance between the 2 spheres. Yeah. And I suppose you have to assume that's the distance to the center of each sphere. Okay, because we have to assume that for Coulomb's law to work. Okay, Coulomb's law is F equals Q1 Q2 over R squared multiplied by the constant proportionality, which was the same one we used earlier. Yeah, so this is what's happening. This is the force we're using. So this is Coulomb's law. K is given to us as 8.99. We want to work out R. Change the subject of the equation, and you'll see that R squared, I made a mistake there, R squared will be equal to KQ squared over F. Yes, so be careful in the exam. It's just a simple algebraic error. R squared is equal to this in the red circle. Yes, not what I've written initially. Okay? So once you got this K, this is Q squared. Yeah, because they told us it's 12 nanocoulombs. That's the charge of each sphere. You have to square them because it's 12 times 12, and then divided by the force, which is given to us in the question. You'll get the separation, the distance between the centers of the spheres, as I was saying, as being 0.051 meters. Again, this time you should write down that you know this is to 2 significant figures. Okay? Not very good writing. I must get an Apple pen because I'm basically using my finger when I use these PDFs to go through the exams. So that's 2 significant figures. It's an old iPad. Okay, I used to use a visualizer camera, and the focus on it went, so I've now used this method instead. I PDF the papers and then scribble on it further as I explain the concepts involved. That's the end of question 17. These you saw as we get to the end of the exam paper, questions 16 and 17 take longer to answer. The concepts are more difficult, but so you really need to get most of your marks in questions 1 to 15 and then see what you can get in the longer questions. So there's still 1 question to go. So don't forget, like, share and subscribe each of the videos, and I'll do question 18, which is the final question, in a final video on this May 2023 Edexcel International A-Level for Physics. Okay, thanks for watching. See you in the next video. Don't forget to subscribe. Thank you.